Okay, well, what I want to do is gas explosion. For the gas explosion topic, of course you will explore more than what we discuss in the class using the gas explosion handbook, or you can expand some content in the gas explosion handbook. For example, today we're going to discuss about the detonation. If you want to learn more, then you can pick up this topic, detonation in gas explosion, or detonation process in gas explosion. Very rare. Frankly, I never study the gas explosion in the chemical explosive, because my concern on research was not detonation physics. Some professor, some researcher spend the whole career on the detonation. And the shock wave is also, you could say, the detonation and shock wave treat as the same, but some they don't. Detonation, the physics who deal with the topic totally work, and the research is different fashion. So if you want to explore detonation in the gas explosion, there's another good topics. Deflagration, book covers that much. I want to really explore some more. Deflagration is a very, very important topics in gas explosion. Then you can spend a whole month to really expand it. And as we're going to discuss here, transition from deflagration to detonation is another topics you can explore. Another topic would be gas explosion and its effect to the plant design. That's another topic. So I wrote papers on underwater explosion, and its effect too is open. You can think of such topics too. Okay, so I want to explore actual accident situation, real accident. I want to explore using the available literature. Some you can really explore and discuss about consequences. What would be the consequences? Then you could refer on the design improvement as a result of your explorations. So there is no limit. I want you to think and get the topics, just the two persons together, discuss together. Then I don't want to just do everything by one person, then the other person idling, which is not appropriate. So that's what I want you to do, okay? Okay, today is a detonation. This could be, I have a book called The Detonation by the two authors. They are pretty well known for detonation. It's that thick, but here is a very short chapter. But the purpose here in this handbook is not giving you complete detail, but you generate lots of topics across the gas explosion, and first to get the comprehensive background. That's the reasoning. And its scope is so much. If I say I know everything, that's a total lie. And this is what I have decided to go through the handbook together this month. So it's only 4 weeks. And the detonation, we're going to talk about the detonation wave, rarefaction wave behind the detonation front. Anybody heard about the rarefaction wave? I think you read the detonation chapter, right? Chapter 6? How come so quiet? Rarefaction wave. What you have in mind when you hear about the rarefaction wave? In this case, as we will discuss, rarefaction wave is the reflection wave from the detonation front. Detonation wave front. That's what you can say. But rarefaction wave is for underwater explosion, we'll discuss next month, is so-called the tension wave. It's a reflection wave is all right, but not the wave reflecting from the rigid surface. So slightly different. So rarefaction wave here you can think of as a reflection wave from the detonation, moving the detonation front. So moving detonation front. And deflagration to detonation transition. Deflagration change to the detonation, which I believe is rarely happening. It's not happening all the time. So that we'll discuss about that. And propagation and the transmission of detonation wave we'll briefly talk. Estimating detonation load. The author discussed about 1/3 of the page, and nothing much learned through this particular chapter. Detonation load, that really means detonation pressure and detonation velocity is important parameters to pick up. And after all this detonation basics, few different manuals exist in chemical explosion, mostly related to the defense application. It has really load versus time, things like that we have. But in gas explosion, I really don't see such a manual for design purposes. So there is a more research to conduct. And guidelines in detonation. So as you read, as I keep saying, don't frustrate yourself, because there are so much unknowns in the gas mixture and the gas explosion. So that's what the nature is. But still, we have a handbook like this. So I think that's really, really good. Again, definition. The detonation is the most devastating form of the gas explosion. Once a detonation occurs, of course, you can't stop. It just happens. So then finish the whole process. It does not require the confinement or obstructions in order to propagate the high velocity. because it will finish the process whether you like that or not. And here a detonation is defined as you know, as we learned, defined as a supersonic combustion wave. That means the detonation front propagates into the unburned gas at the velocity higher than the speed of the sound. Speed of the sound in front of the wave, or unburned the gas, or unburned mixture. Remember this. And detonation velocity is about 1,500 to 2,000 meters per second. So, which means water, the water media, acoustic speed in water media is about 1,500 meters per second. So even around the water, the acoustic speed, it passes around there. Because we don't know what the unburned fuel is, acoustic speed in the fuel could be changing. But as a measure, as you see water, which is 1,500, and this is higher than 1,500. And peak pressure is 15 to 20 bar. So this case is, of course, a dynamic pressure for gas explosion. Chemical explosion, a lot higher. But for the gas explosion, 15 to 20 bar is a very high pressure, usually around the 5 bars. So, you know, lots of things you read already, but some important paragraph, as I always does, I use a bold. This detonation wave, it just refers really a couple paragraphs. The Chapman and Ugart is my pronunciation may not be true. This person is around the year 1900. They were actively involved in the detonation work, and you can access their papers possibly. I tried it. I saw a cover of the papers, things like that. But you can, if you gonna work on as a part of the the October project, that would be also good topics to really revisit the CJ, the theory on the detonation front. And this is not the complicated mathematical the exploration. So it is well known nowadays as a CJ theory for detonation, the wave front. And of course, this is a really one-dimensional theory they developed. So as shown here, using the conservation equation for mass, momentum, and energy across the one-dimensional wave. For the water, underwater explosion, as we're going in November, using the conservation law, we are going to derive the equation for the wave velocity and also the pressure. So you will see that there. That's one-dimensional. You could expand into two-dimensional. We did also there vice versa. So this book written by Fickett and Dave is what I have in my office, and very mathematical. So this is, we're just going to use as a C-J theory, which means developed by this two-person in 1900. That's the beginning of a detonation work. That's all you can think of. And of course, this is a fuel type of the fuel dependent. Here is percentage of ethylene in the air from 0 to 20%. And this is CJ detonation velocity is really not equivalent to saying the detonation velocity. The CJ developed using one-dimensional mode, so they always use a CJ. It's calculated, the detonation velocity, meter per second. Here is a CJ pressure using the bar. And for the particular fuel, the ethylene, and you may be able to find for different type of the fuel. This is for this particular type of the fuel, ethylene, and velocity, detonation velocity, and detonation pressure. So the red, the black is velocity here, which is about 1850 meter per second. And for pressure is concerned about 19 bars. So pretty high. So for that particular fuel. And they introduce, they are dealing with a few different fuels all the time. This is really, I don't know the detail of this, but they are dealing with here is, of course, it's like a tube here, and this is a burned gas, this is unburned gas. Right here, there is a reaction zone right here, which is really detonation wave front. And this is expanding form of this reaction zone. And this is a shock wave front here, and this is a behind of the shock wave front, and very thin shock wave front. It's not thick. And they're dealing here is a cell size, lambda. This cell size, I don't know how they really measure the cell size, but that's again depend on the type of the fuel. So cell size is different. And detonation pressure type and velocity is also the function of the cell size. So cell size, it varies, as you will see, it varies from the millimeter to 1,000 millimeter. So that portion, you again it give a very simple geometry, and even discussion materials are simple here. But in front of the shock wave, this is undisturbed, unburned gas, and it's like a fish shell type. And this is so-called the stem, shock wave stem. When you say tri stem, when you call that, that's really like this. This is some boundary. This could be rigid or flexible. And when the shock wave comes, it's gonna be something like this. Wave gonna go hitting it, and the reflection wave comes right back out here. And it depends on the velocity and the motion of the boundary. And what this could propagate is something like this. This point may not stay right at the contact. This is like it's called a tri-point, something like this. And this is coming down, and this wave is go up. And it generates a stem. Stem usually propagate in the direction. It's called, I think, a tri-stem, as I recall. And it generates this. When this is really flexible, then this type of the junction really forms up. That's what over here, when they talk about the stem, this is what they are talking about. Even I feel this kind is tri-stems. Possibly this kind is the tri-stem, the vice versa. And the J&D theory is three authors, Russians, von Neumann, N is U.S. author. D is Doring, I think European. They really developed the theory in slightly different type, but eventually they all put it together and called the J&D theory. So again, the couple minutes talk I tried to do here is not enough. So J&D theory is a pretty well-known theory, but if you really get involved in detonation, it may be a good idea to getting into the detail. But detonation, again, may not happen all the time for gas explosion. In fact, it rarely happens. For some fuel, it doesn't happen. But very sensitive the fuel, like hydrogen, it happens. It has some discussions, small discussions on that. Again, this is a different type of the fuel, maybe. And detonation cell size is a millimeter. From 1 millimeter, you're going all the way to 1,000 millimeter for the hydrogen, ethylene, actylene, and this type is a very sensitive fuel, and this type of the fuel, they can have a really detonation. Other types, it rarely happens. That's what the handbook claims. And percent of the fuel in air, 0%. And 0%, what does it mean, 0% the fuel? Which means it's all air. But they're not dealing here, is in this range, around the 5% fuel. So it's gonna be, it starts around 5 or 4% of fuel. And you can see how the hydrogen behavior and other fuel behave there. Some good example, the handbook is really showing. And always, it happened to have a measurement environment in air, 25 degrees C. This is nominal temperature and nominal pressure. So this is what the air pressure is 1 atmospheric pressure. And this is another type of the fuel, propane, methane, ethylene. So that's what they're talking. Rarefaction wave behind the detonation front, rarefaction wave. So it shows right here. So this is a tube-like, this is a fixed end, and this is through the open-end tube. And this is like a detonation wave front here, and always discontinuous wave front. And the maximum pressure here is CJ pressure right here. And behind the detonation wave is called the rarefaction wave, is caused by the reflection wave from the detonation wave front. And about half of the length of the tube here, measured this point as a 0, this is half the L, this is L here. This is where L is where the detonation, the front occurs here. Then pressure reduction going to happen here due to the reflection wave, which is called the rarefaction wave when it's reflected from the detonation wave front. And here is when x is equal to 0, this is fixed, and the velocity of the wave is 0, doesn't move. It usually ends at half the size of the tube here, measured from the detonation wave point here. And detonation wave is sitting right here, and this is undisturbed, unburned gas, and this is 0 speed, and this is 0, not exactly 0 here, but that's what they claim you can assume. And here in this range from here to here, then U is not equal to 0, it's larger than 0, where the rarefaction wave pressure is higher than 0. But this is the static pressure, which is about 40% of CJ pressure. And in front is just a static pressure, nominal pressure of the unburned fuel. Some basic discussion. I just put the tube here, this range, this is a tube they are dealing with. There is no additional information I could find. I tried to find it, but there is no any other additional information on this rarefaction wave behind the detonation wave front. This is all discussion about that figure. Okay, then this is a deflagration to a detonation transition. As it mentioned here, when the deflagration becomes sufficiently strong, a sudden transition from deflagration to detonation can occur. It said it can occur. Not always occurs. So it's a little bit fuzziness is there for gas explosion that you have to think. And it shows a few example cases which it happened. such a transition from deflagration to detonations here. The author claimed this has been observed in the several experiments shown below here, and it involved the reactive mixture such as acetylene and mixed with air, and hydrogen mixed with air, and the fuels with oxygen enriched atmospheres. So such sensitive fuels, such a transition could happen. That's what few different experimental results they are discussing here. You can read. Okay, 3. And this is what the discussions on that. And there is sort of the concluding remarks here. From a practical point of the view, it is important to recognize that the transition to detonation will cause extremely high pressure in the area where the transition takes place. When the deflagration really changed to the detonation, tremendous pressure right around the transitions happens. So if it's a piping system, it could burst out. That's what they are claiming here in the next couple of pages. And this particular figures is pressure time profile from the pressure transducer located close to an area of transition to detonation. This is where the shock wave, sudden jump of the pressure you observe. And this is not the detonation point, and it's keep increasing. At a certain point, the pressure jump up here, around here, then that's the detonation time, which is measured in the microsecond here. So this is really expanded, 2,500 microsecond to 2,600. So from here to here is about 100 microsecond, 10 to the minus 6. So detonation range is around here. And this is the case when the transition to detonation occurs. This is the area the transition is happened here. For the tube, it could burgeon in some certain area. But I never know. I never saw such a result of the experiment, but in reality, by the accident, or the tube can have a fracture, possibly. But really, I didn't see in the accident. Maybe if you, in the future, you could see such a burgeoning, then you can think of high pressure buildup by the detonation. Then in conjunction with particular the pre-mixed fuel. So that's what you can think of. It's said it's a case history. If you read the previous page, it shows the case history also. You can think of that. And the propagation and the transmission of detonation. So from the deflagration, it give a transit to the detonation. When the detonation happens, even in the short duration of the time, it could propagate the detonation wave. Front will propagate and it transmits all the way through. That's what 6.2, 6.3 is talking about. And in this particular section, they claim two parameters is very important: geometric conditions and size of the cell. Size of the cell is depend on also the type of the fuel, and geometric condition means whether it's a tube or it's a channel, open channels or closed channels, or confined or unconfined. That sort of the conditions is what you are talking about it here. And here is a requirement. It's a requirement for successful propagation of a planar detonation in pipes and channels. So this is a pipe, and one condition to have a successful propagation of the detonation wave, here is a detonation could occur. This is pipe diameter. If D pipe diameter is larger than at least 1/3 of the lambda, lambda is a cell size. Okay, in the section 6.2 is talking about the cell size in the detonation wave front. And this is a channel. This is like a square channel. H is height of the channel. If it's larger than lambda, then successful propagation happens as a planar, the detonation front. This is like a long width. So in this case, it's the same conditions imposed in there. So this is a planar detonation for channel case. And another case they are dealing here is, again, for successful transmission of planar detonation into an unconfined three-dimensional spherical detonation wave. What that really means is a three-dimensional, and for the transmission of a successful planar detonation is unconfined, which means it's open, unconfined. There is no restriction, limitation for geometric condition. When it exits to the one side here, it generates a spherical, the wave front. Spherical is at the detonation as it exits, and conditions for the D diameter has to be larger than 13 lambda, and this is 10 lambda, this is 3 lambda, vice versa. So it's a specific geometry, but I don't think you will ever face this situation because the geometric condition for particular plant you are facing, you don't know, I don't know, of course. So, but such a considerations, if you have keep that in mind, then when the situation arises, you can think of for detonation in conjunction with the gas explosion, not the other type of the explosion. It's only gas explosion. It doesn't happen really air explosion. Air explosion doesn't happen. Air explosion is next to chapter, which is blast wave. At least to give you the taste what the important factor is there. That's what is good idea to keep that in mind. This is a requirement for propagation in unconfined cloud, means gas mixture, as shown in this figure. And really, this is the detonation, the wave front. This is all open, unburned. This is burned gas, and as it generates the detonation front here, and this is unburned fuel air cloud is moving along. It's unconfined situation. Estimating detonation load is, they're talking about the Stan Gen. It said one professor in Stanford looked like developed. It's in the reference. Frankly, I never heard this Stan Gen code. Anybody heard about Stan Gen code? Never heard. But if you have a chance, take a look at the references. You can go into exploring the Stan Gen code. But detonation load is what the Handover claim to look at. And the guideline on detonation, it has a few paragraphs. One of the paragraphs is the probability of occurrence of a detonation in fuel-air mixture depends strongly upon the type of the fuel. We keep talking about the type of the fuel. Type of the fuel is the first thing to identify to explore the phenomena. If you don't know the type of the fuel, there is nothing to start with. So here it said very reactive fuel is hydrogen and acetylenes and ethylene. And it said may detonate in an accident situation pretty fast fashion. And it mentions also here saying other fuels are less likely to detonate. You see, other fuel, except this, like a 3 or 4 sensitive fuel may not detonate. In particular, no data exists on detonations involving pure methane air. Methane is classified as a low reactive material, but still don't have, maybe this is really up to about the early 80s, maybe up to mid 80s. So up to that point, maybe no data exists, but now after 20 years, we might have some data exist. So methane is popular fuel. So if you go look at, you may be able to find in conjunction with the detonations, okay? And the most Stan Gen, they're talking about it, and that's about all it mentioned here. Okay, so detonation discussion, really I'm not that happy to myself to discuss, which I never experienced myself, but idea is let's gain some understanding of detonation in conjunction with the gas explosions, okay? So I think that's sufficient for a time being. Then as you get if you want to have more information, you can really explore.